Well, first I want to thank Ariel and the organizing committee for the school for inviting me to talk today. It's great. And also thanks to Terry for the promotion and the introduction to what I'm going to be talking about today. Today, I wanted to guys just walk you through the process of how we, for the last few years, have been analyzing mainly Hawk Plus data in order to extract information from the magnetized turbulence. Right? So looking at this image of polarimetric data at the 53 micron from Hawk Plus, here, one of the things that we know by fact is that the dust polarization traces the magnetic field. Okay, that's the basic of our, the work that we do here with far infrared polarization. Now, what we really are interested is in whether the specific patterns that you can see on observations like this can tell you actually a little bit more than just the direction where the magnetic field is locally. So we can see on the right an example of the two cases. If the magnetic field in this observation in particular is strong, you can see that the dust particle will have no really strong chance, okay, of moving them too much, of modifying the morphology in this case. But in the case of having a weak magnetic field, you can imagine that if this magnetic field, of course, is embedded in a medium that is turbulent, then the dust particles will be moving about and dragging the magnetic field with them as well. So what we want in this case is, okay, given the observations that we have, given the patterns that we observe on these polarimetric maps, how can we then tell something about the strength of the magnetic field in this case, all right? Now, for this, this was actually an idea that was, conceptualized in the 50s, actually by different people. I believe Davis worked separately from Chandrasekhar and Fermi. However, they arrived to the same conclusion. And the idea is relatively simple. The idea consists that if you have a magnetic field, let's say, in this sort of like curve shape, and this magnetic field somehow, you can probe it by these polarization vectors, okay? You can then assume that the specific pattern that you see in polarization vectors is the result of an Alfvén wave established in, or an Alfvén wave established in the plasma, in this case, right? And that the velocity of this Alfvén wave, specifically the amplitude of the velocity of the Alfvén wave, is proportional to the amplitude of the temporal variations, in this case, measured by or related to the velocity dispersion in the gas, and inversely proportional to how much these polarization vectors are being deviated from the large-scale magnetic field, right? So with this simple idea, I think, saying that the velocity is proportional to this term, and knowing that the velocity of an Alfvén wave is also proportional, like the definition just from theory, is proportional to the strength of the magnetic field unperturbed, divided by the root square of the density. You can then put together these two expressions and arrive to a very simple approximation, which is the DCF approximation, the DCF methods. It's relatively simple in the sense that all that you need to calculate the strength of the magnetic field is to have a notion of what the mass density in the medium is, what the velocity dispersion in the medium is, and the angle dispersion as well. Okay. However, there are many considerations and limitations that you need to keep into account when you use the DCF method. Yes, it is simple, and it is also powerful, but you have to know the limitations of what are the conditions that comes attached with this. Some of the considerations, things to keep in mind, is the fact that when you are estimating the magnetic field strength in these using this expression, for example, you are only calculating the component in the plane of sky. All right. Indeed, the DCF approximation will not work if your magnetic field, the three-dimensional magnetic field, is really, really close to the line of sight. All right. Now, the other thing is that the velocity dispersion is assumed to be isotropic in the sense that it doesn't matter in which direction you look at the turbulence, this velocity that you include in this expression, it will not change if you look at it in the plane of sky or the line of sight. And that's actually the principle that allows us to use this expression. All right. And finally, a really, really important thing, it's the fact that the angle dispersion that you need to introduce in this expression has to only take into account the effects of the small scale turbulence, all right? So if the magnetic field itself has a shape, a really big large scale structure, that also introduces dispersion in the angle that we don't want to have. We don't want in the when you introduce those values in this expression, because you will get more likely overestimated values of the magnetic field strength. On the other hand, some of the limitations of this simple model is the fact that many people have tried to do correction factors or calibrations of this, and the latest done by Liu et al. Using simulations as a simulation said that this correction factor in some cases can be between 0.25 or 0.50. In terms of like the magnetic field strength that you can calculate with this and compare it to like a reference value or a true value. And on the other hand, there's also a lot of suggestion that says that the DCF method has to be very carefully used or considered in certain conditions, like for example, when the turbulence is superalbenic. I think this is a typo, and or what I'm trying to say, it only works in certain conditions. In this case, mostly in superalbenic conditions. Now, as I mentioned, the ingredients that we have, we need to use the DCF in this case are three: mass, velocity dispersion, and angular dispersion. This is an example of how we normally obtain these ingredients. In the case of the mass density, we prefer, or we have more experience on obtaining the mass density by means of obtaining the column density. The column densities can be used or can be obtained for a specific observation, basically from if you have you have observations of the same target at different wavelengths. This is an example of a work by Chess et al. In 2019 that for OMC1, in which not only the 4 wavelengths of Hawk Plus, but also combined with some Herschel and other instruments, were able to characterize the spectral energy densities for the entire region of OMC1. Okay, so this is one of the ways, or it's the way that we use the most to find the column density in this wave, but also depends on whether you have appropriate observations. Now, going from column density to then number density, you have to have a notion of how deep is the cloud. You need to have that some idea of the third dimension in that case, and which it can prove to be difficult in many cases, and we'll see that. And finally, the mass density is just obtained by multiplying that number density by the mass of the hydrogen and the mean molecular weight in this case. The next ingredient in the DCF approximation will be the velocity dispersion. We have what you really want to do for this case is to use a molecular tracer that basically is in sync with the dust, that leaves where the dust is, and that traces very well the structure of the dust. We have had good success using ammonia line and multiple carbon lines in this case. The thing, of course, what you want to see from this molecular lines, of course, it's the spectral structure. You want to see these lines or lines, spectral lines like this, because it is the width of these spectral lines that will give you an idea or of what is the velocity dispersion in this for your observation. Now, in some cases, in particular, carbon lines, you need to take into account that they might also include a component that comes from the thermal motion of the gas in this case, and then you can correct it basically by knowing what the temperature of the cloud, or assuming certain temperature for the cloud, and using the mass of the species in particular that you have. And more importantly, also is to take into account the difference between the observations, beam size or resolution for each one of these ingredients, all right? Because in other cases, then you'll be, combining observations with different resolutions, and then you can overestimate or underestimate the magnetic field strength that way. Okay. Now, on to what I think is what require a little bit more work of the DCF ingredients, which is the angular dispersion. Also, because it's probably the one ingredient that I spend a little more time with. As I mentioned before, okay, the fact that we have in many observations, in many of these astrophysical objects, you will observe magnetic field that has this a large scale structure. Let's assume that is some form of curved magnetic field in this way, that if the magnetic field was not in a turbulent medium, the polarization vectors will just trace the magnetic field, the large scale, easily. All right. Now, the thing is, like, this shape in particular of the large scale field will provide you a measure of angular dispersion, just because the magnetic field is not uniform in space. Now, when you introduce the turbulent motions in the magnetic field, you'll see that the polarization vectors will deviate from that large scale field, and will provide also a contribution to the angular dispersion in this case. So a way to see it will be this way, this equation that I have here. Your measure angular dispersion, or dispersion of your polarization angles in this case, will have a contribution that comes from the magnetic field, the large scale of magnetic field, and a contribution from the turbulent part. And as I mentioned before, then what you would really want is the second term. You don't want to take into account the first term for the DCF approximation. So the questions kind of the problem reduces to, okay, how do you remove the large scale contribution in this case? And two methods that I want to mention are one used by a group that works primarily with the bistro the Bistro survey, or its polarimetric data in 815 micron from the JCMT, and the method that I'm more familiar with in this case, which is the structure function. Okay, now the Ohm sharp masking method basically it tells, or the idea behind it is that if you have a polarization map like this one here, you can smoother a little bit, okay, to try to infer that large scale structure. Basically, if I smooth it a little bit, I can get rid of that turbulent deviation, and therefore the difference between these two maps will give me that turbulent component that I want, basically. All right. In this case, we see the example of for OMC1, specifically close to the BNK object, and in which they apply this, and then once you have this. The deviations of the magnetic field from this found large scale, all right, well, then you can calculate just a simple standard deviation value of this residual orientations. Now, in this case, for this method in particular, then you have the free parameter of choosing what the smoothing kernel will be, and two considerations I think that needs to be taken into account when you consider the size of the kernel is that if you have a kernel that's too small, for example, below the size of the observations beam, then you will be sort of smoothing smoothing vectors that are correlated to each other. So you need to have, in my opinion, a minimum kernel size that will be limited by the beam size. And now for the maximum size, it's basically, or what you can do, or actually what they do in Patel et al. 2017, is to determine a more optimal, the most optimal size of kernels that basically will recover a true dispersion value from a toy model without being big enough that you basically blur the information too much because of this large structure that you have there. So in this case in particular, although their method is well calibrated to work for a certain size of kernel, I think that in this issue in particular, the structure function method it's a little addresses this idea a little clearer. The structure function or dispersion analysis basically takes calculates a structure function of the difference in angular on polarization vectors direction. So basically what you do is you take this vector here, for example, and this vector here, this is a pair of vector, and you calculate the difference between these two guys. And that difference, it's parameterized, or it's characterized by the distance, the isotropic angular distance between the two of them. So what you do is you literally repeat this process for every possible pair of polarization vectors that you have in your observation. And then in order to construct or to have a single parametric function, you beam this difference, or the cosine of the difference of this angle into certain values, or you basically take values of L, the angular distance on the plane of the sky, and calculate the average over those beam of L. The result of that is just a function that it's just depends just on L, the distance L, the angular distance, isotropic angular distance in the plane of the sky. Of course, this function in particular that we have here this dispersion function also contains the two components, or also has traces of the two components of large scale or small scale magnetic fields in this quantification of the dispersion. All right. So the way that Hildebrand and Hurel model this dispersion function was by saying, all right, so we know that it depends on L, so we can then expand in some form of Taylor series and then cut at the L square term. All right. Now the L, just the linear term on L is not really relevant in this case, but although basically the model that they use to describe this structure function is it's just basically this term that include or describe the large scale order contribution, and then a small term here that also depends on L that has the contribution from the small scale and turbulent part. Now, in order to model this term in particular, which is the one that will give us the information that we want for the DCF, they assume that the Gaussian turbulence, or the turbulence at this scale is small, at this small scale is Gaussian in form, and that the beam itself also is Gaussian. All right. So after doing two papers of math, they arrived to this expression here. And what exactly this expression is telling us here, especially in the first term, it's just telling us that the observed dispersion in the form of this function that we constructed has a contribution in the small scale that has to take into account the fact that the turbulence is Gaussian, which is will be this term here, but that also taking into account that the polarization observation will be integrated or take into account the fact that it's integrated over the beam size, or the observation beam size. Now, these parameters that we have here characterize the magnetized turbulence in this small scale. Some of those parameters are the number of turbulent cells along the line of sight, the ratio of the magnetic field energies between the turbulent and order components of the magnetic field, the correlation length of the turbulence, and in this case, W is just the size of observation beams. The definition of the number of cells along the line of sight includes basically the size or involves basically dividing the depth of our cloud in small units or small cells that are characterized by the size of the turbulent cell, which is delta in that case. And this capital delta prime is what we call the effective depth of the cloud. All right, so how does the dispersion function basically looks like this? All right, for the case that you just calculate for every single pixel that you have in certain observation, but we're not really interested in the tail of this dispersion function. Indeed, we just want to concentrate on the small scale of the part here that we can describe with the model. When we zoom into this part, we see then this will be the dispersion function as a function of L squared, and this will be as a function of just L. All right. The reason why I present it this way is because in order to observe exactly just the term that is related to the turbulence, you can first feed this equation with an L squared term, linear term in this case, or L squared in this term, for a certain range, and then that feed can be subtracted from the dispersion function to observe specifically this part, or the turbulent small scale part of the dispersion function. The amplitude of this function should tell you that the information that we have or that we want for the DCF. However, that integration along the line of sight, or the information, the fact that this the polarimetric observation has information along the line of sight about the integration along the line of sight, and also integration of the beam size, makes this value to be underestimated. Okay, so what we want to do is somehow correct the amplitude of this function here. On the other hand, this will be that turbulent component that I've been talking about, and this function here in gray will be just the beam size. And what you want to do, what you want to see is your turbulent component to be wider than the beam size, because that means that your turbulence has a scale that is bigger than that, that the beam's observation. Therefore, you can resolve the turbulence with your instrument in particular, all right? So you always want to have delta values that are greater than certain, actually greater than root square of 2 of the beam size. Yes, the beam, the observations beam, all right? So, as I said, basically what you want to do is to take that amplitude of b squared and then multiply by the n factor that we determined before. That will give you an idea of what this sigma phi is, or the angular dispersion. And with a little bit of work, then you arrive to the fact that the angular dispersion is just related to this fraction of the magnetic field energies, right? And if you introduce that into the DCF approximation that we had from before, it just turns into this case here. You see that in this case, it depends on the root square of this parameter, all right? Now, of course, the example that I showed before, from these fits, from basically fitting these functions that we have here, we can obtain those parameters that we are interested in to fully evaluate this DCF expression. Now, the examples that I have in this case, let's just check how much time I have. Okay, I have about 5 minutes. First was work done by Chess et al. In 2019, in which we applied these methods to the OMC1 region. Because of the richness of the observations from Hop+, you know, we were able to actually split the OMC1 region into these 3 regions that we call the bar, the H2 and B and KL, and actually characterize the magnetic field strength and turbulence in each one of them. And we saw that actually these are regions that have completely different magnetized turbulence conditions. All right, so this basically made us think of, okay, so how can we actually like go? How can we actually or made us interested in having more details about the magnetized turbulence or magnetic field strength in this observation. Now, so we moved to applying this this technique on a sort of moving kernel situation, in which we center in one pixel, define a kernel around which we construct this dispersion functions, and then fit them and find the values of the ratio in the values of the region, so we can construct maps of the magnetic field in this region. Of course, for this case, what we have is in order to basically use the DCF approximation, because we're not talking about simple numbers now, you'll have to be using maps for each one of them. Keeping in mind that maps obtained with different instruments will have different angular resolutions. You have to put the 3 of them in this case in a common resolution to then combine. And the results were these maps that we see here, right? And the maps like this, as Terry mentioned in his talk, will allow you to construct things like the maps of magnetic mass over magnetic flux and things like that. But it also allows you to see further details in this in your observations in terms of the magnetic field, and in combination with your with the orientations, it allows you to further explore, all right, and understand the conditions of your target. Now, a particular example that I wanted to do, like, it's one of the things that I like about using the DCF method in with the dispersion analysis is that it doesn't have to stop when you calculate a strength of magnetic field. A good example is the magnetic field in the starburst galaxy M82. What SOFIA Plus observed in this case was a magnetic field that was very perpendicular to the plane of the plane of the galaxy, but because we also know that in this galaxy has this flows of material going in the same direction of the magnetic field, we were interested in knowing what was the interplay between magnetic field and flows in this case in this galaxy. And the first thing is that these are slightly different conditions for an outgoing wave to live. Therefore, we had to go back a little bit and think, okay, how the presence of a large scale flow along the magnetic field will modify the velocity of an outgoing wave. And after doing a little bit of math, we can actually arrive to a correction of the Yes? I'm sorry.
I think someone unmuted, but actually, yeah, just if you could wrap up soon, because we're...
Oh yeah, yes, this is my last slide. We can actually correct the magnetic field strength from the DCF by knowing the certain value of the large scale structure. As using this, we were able to extrapolate the magnetic field strength that we have in the core of the galaxy, farther out, and we can see that these lines are, pretty open in this case. Now, I just want to leave this here. I just want to conclude this talk, with the fact that although the DCF method has a lot of considerations and limitations, the more we use it, the more we know that or we know of these limitations, and we can address them in this case. So of course, it's always good to know that there are other avenues to compare, for example, of how to find magnetic field strength. And if you have any questions, I'll be happy to try to address them.